Welcome! So, for this explainer, we're going to do something a little bit different. Instead of just talking about a machine learning algorithm, we're going to actually crack it open and look at the Python code that makes the whole thing tick. And our subject today is linear discriminant analysis, or LDA. And hey, to make it interesting, we're going to use it to tackle a classic, pretty high-stakes question. Can a relatively simple line of code actually predict whether the stock market will go up or down? That's the challenge we're setting for ourselves. So let's jump in. Here's our game plan. First, we'll set up the market prediction problem. Then we'll introduce our tool. That's where the code meets the theory. After that, we're going to pop the hood and look at the math, see what verdict the code gives us, and finally, talk about what it all means beyond just a single accuracy score. All right, first things first, the problem itself. We're going to set up a classic classification experiment, and we'll be using a pretty well-known data set called SmartIt. So our goal here is super specific. Can we predict if the market's going to go up or down on any given day? And the only information we're going to give our model are the percentage returns from the 2 days before, which in our data are called lag 1 and lag 2. Now, before we even think about building a model, we have to do something absolutely fundamental. We split our data. We're going to use all the data from before 2005 to teach our model the patterns. We call this the training data. Then we'll keep all the data from 2005 separate to give our model a kind of final exam. This is our testing data. It's a really crucial step to see if our model actually learns something useful or if it just, memorized the past. Okay, so what's the tool for the job? We're going with linear discriminant analysis. And this is where we're going to see how a single line of code is really just the tip of the iceberg for all the statistical theory underneath. In the popular scikit-learn library in Python, this is pretty much it. This one command, LDA.fit. You just pass it your training features, our lag 1 and lag 2 data, and the training labels, the actual up or down directions. This single line does all the heavy lifting, all of the learning. But that's the real question, isn't it? It kind of feels like magic, but it's not. What is this .fit command actually doing? What math is it running under the hood to learn from all our data? So let's find out. This is really the core of what we're doing today. We are going to connect the outputs from that Python script directly to the statistical concepts that LDA is built on. It's time to open up the black box. So when you run .fit, the LDA model is essentially calculating 3 key things from your training data. First, something called the priors, which is really just the overall proportion of up days versus down days. Second, the means, which is the average lag values for each of those groups. And third, and this is the most important part, the scalings. These are the coefficients that actually define the line that will separate our two groups. Okay, first up, the priors. If we actually look inside our fitted model, the prior scores attribute gives us back 2 numbers, 0.492 and 0.508. And what this tells us is pretty simple. In our training data, 49.2% of the days the market went down, and 50.8% of the days it went up. This is basically the model's baseline assumption. It's the starting guess it has before it even looks at the specific lag 1 and lag 2 data for a given day. Simple as that. Next, let's take a look at the means attribute. This attribute is going to show us the average value of lag 1 and lag 2 for all the down days, and then for all the up days. You can think of these as the center of gravity for each group. And what's really interesting here is the pattern it shows. On days the market went up, the previous day's returns were, on average, slightly negative. And the opposite is true for days the market went down. The model is already picking up on a subtle little trend there. And finally, we get to the most critical piece of the puzzle, the scalings underscores attribute. The code spits out these 2 numbers, -0.64 and -0.51. These are the secret ingredients. And this slide illustrates perfectly what those numbers mean. They're the coefficients, the weights, in a simple linear equation. LDA takes our predictors, lag 1 and lag 2, and uses these weights to cook up a single score. This equation defines the decision boundary. This is the line that LDA has learned to draw to best separate the up days from the down days. So we've trained our model, it's learned the priors, the means, and most importantly, the line to separate the classes. So now, it's time for that final exam. Let's make some predictions on our 2005 test data and see how our simple line actually did. The results get summarized in what's called a confusion matrix. Let's just break this down real quick. The rows show what really happened, and the columns show what our model predicted. So the numbers on the diagonal, the 35 and the 106, that's where our model got it right. The other numbers, those are the mistakes. For example, you can see the model predicted up 76 times when the market actually went down.
So, if we add up all the times we got it right and divide by the total number of days, we get our final accuracy score, 55.95%. It's better than a coin flip, but only just.
So there's our number, almost 56% accurate. But is that the end of the story? I mean, is a single number ever really enough to judge how good a model is? Let's dig a little deeper. This quote from Introduction to Statistical Learning, the textbook this whole thing is based on, makes a really crucial point. It uses a different example about loan defaults, but the idea is the same. Sometimes the type of error you make matters a whole lot more than just the total number of errors. For a bank, failing to predict a default is way more costly than maybe flagging a good customer by mistake. And that same logic can apply to the market. It's also really important to remember that LDA makes a big assumption that a straight line is the best way to separate these groups. But there are other tools out there, like its cousin, quadratic discriminant analysis, or QDA, that can actually draw more flexible curved boundaries. LDA is just one approach, and we chose it for its simplicity and its linearity. So the key takeaway here is that LDA's power is really in its simplicity. When you type LDA.fit, you're basically asking the machine to find the single best straight line, or, a flat plane if you have more dimensions, that it can use to separate your data into these different groups. And that brings us right back to our big question. We use a simple linear model, and we got about 56% accuracy on an incredibly complex problem. So, what does that tell us? Does it mean the market is almost, but not quite, random? Or does it just mean we need much more complex models to find a real signal in the noise? Well, that's something to think about. Thanks for joining me.